and we can start. So, hello everyone. Today we are very excited to host in our CUSP Spring Research Seminar Dr. Roberto Andrade. Roberto Andrade holds a bachelor's degree in physics from the Universidad Federal de Bahia, a master in physics from the Universidad de Sao Paulo, and a doctorate degree in physics from the Universidad Regensburg. He was a postdoctoral fellow at Free University of Brussels, Belgium, and Potsdam Institute for Climate Research in Germany. He was also a visiting professor at several institutions, including Oldenburg, Coruna in Spain, ETH in Zurich, Switzerland. And after serving as a statistical physics professor at Federal University of Bahia, Andrade continues to develop academic research activities and supervise doctoral theses in this institution within the prop-up UFBA program after retiring in 2019. He's a researcher at the Center for Data Integration and Knowledge for Health, CDEX, of Gonzalo Moniz Institute, Fiocruz, from 2017 up until now, and served as the General Secretary of the Brazilian Society of Physics. His interests lie in statistical physics and complex systems, with contributions on aperiodic magnetic models, hierarchical lattices, nonlinear dynamical systems, complex networks, self-organized criticality, analysis of complex systems in biology, economy, climate, and geophysics, and the use of big data to analyze health outcomes and disease spreading. With that, I would like to thank Dr. Roberto Andrade for joining us today. He will talk about scaling properties of urban health and urban infrastructure in Brazil and Latin America. Let's give a warm round of virtual applause to our speaker.
Okay. Thank you very much, Sharon. It's a pleasure for me to be here, and thank you very much for the invitation to present this, the rest of some work. As you said, I'm going to talk about scaling properties of urban health and urban infrastructure in Brazil and Latin America. I would like to start showing the team. I'm going to talk about two works, results from two works. They were obtained by a collaborative group of people that were at SIDAX. These are their names here, and people from the Salubal project, which is a multi-center project hosted at the Drexel University in US. And there are some people of SIDAX that were also part of the Salubal project as myself. And then, so I list here some key persons from the Salubal project who also co-authored these two works I'm going to talk about. Here are the first page of the two works. This one published in PLOS One, and the other one appeared last year in Science Advances. Okay. So this is the summary of my talk. I will try to go through these ideas. Okay, and if you want, you can interrupt me at any time. I will be ready to try to ask some questions if you some points that are not sufficiently clear for you. Okay, so we start with the urbanized world. This effect of our days. Okay, with these numbers that we are facing already for some time. 50% of population living in cities. Here we want to say and try already to present a definition of what a city is. It's very difficult to provide a, a definition, but we only characterize here. We say it's from 5,000 to over 20 million people is the size of cities. They allow for complex social interaction among individuals, and it's already known from that living in cities, it is a form of living that the humanity evolved to, okay, living in cities. Mostly people believe, and I do also, that great advantage for economy, infrastructure, service, creativity, and assistance programs. Okay, so it's better, it's more, at least for considerable part of the population to live in cities. However, you also know there are some problems. Okay, you have a payoff here. You have criminality, you have pollution, and changes in the way people live. Also, this also impacts on health. Okay, this is slide shows why I am interested in this kind of problem. At SIDAX, we are trying to understand several dimensions of health, how health impacts the life of people, and urban health, as we say, is also then one issue that we try to understand here at SIDAX. Okay, my point of view to reach these problems is from a point of view of complex systems. I would like to, when we call here a complex system, we refer to a system with a large number of agents. In physics, we say degrees of freedom, and they interact in an open system, and they, in physics again, they generate and they produce, they consume energy that they also reserve and evolve to optimized form. Okay, some of these forms are somehow universal. This concept of universal is very crucial at this moment, although we cannot give such a very precise definition here. We say, but this is a word that's commonly appear when you talk about scaling in complex systems. Okay, scaling concepts is an important pillar. Okay, there are several theoretical aspects in many areas of physics where people think that we see that some systems they look like others, but some traits of systems look like those of other systems, but they are different in size, for instance. And so scaling is mostly related how when increasing the size of one system in comparison to a similar system, due only to their size, how these properties are related. Here, one of the first laws or first systems that were systematically investigated were about allometric scaling relationships in living organisms. And this Kleiber law is a well-known example for how the metabolic rate of organisms change over with the mass of organisms. This is the famous 3/4 law, and this law is found to be valid over a very wide scale, from mitochondria up to whales. Mitochondria inside cells up to otherwise, there are some also detailed allometric studies that focus on other aspects of living organisms. And there we find, for instance, that the life extent, the frequency and number of heartbeats, they also scale according to a precise exponent, but they somehow they may depend on specific clades, on groups of organisms. Okay, they are not such as universal as this metabolic rate here as Kleiber law. Then we consider that some seminal works by these authors that consider that cities may be seen as organisms, okay? And so if it's seen as organisms, you can also conjecture whether they would present some kind of scaling relationships, okay? Similar to those observed by actual organisms. And then this is what this kind of research, the kind of work I'm presenting here has to do with, okay? We think we do the same kind of search for allometrics of scaling relationship that links some indicators of that are used to characterize a city with the size of the population that lives in the city. A major issue that arrives is then whether these two statements are okay or not, whether we can the scaling is such universal that all cities in all countries, okay, obey the same law, or whether there are some influence of local aspects, of cultural aspects, of climate aspects that make cities look different from one place to other, okay? But this is an issue that we are going to discuss here, how they can, or they, in what extent they can be as wide a concept or not. Okay, that's then what I just finished to say, whether they, and then we decided to work here with two systems. I have a systems of cities in Brazil, a data set of cities in Brazil. This kind of work with aiming at regional heterogeneities can be done for big countries like those here, okay? And so we can do this. On the other hand, the other work relating health outcomes with the scaling properties of health outcomes with city size, we do it with a different data set. Cities with more than 100,000 residents in the US and also in 10 Latin America countries. That's where the Salubal project I refer to provided this data, okay? Here we do several kinds of detailed investigations, okay, for causes of death. We the mortality scaling, both all cause mortality, but also to some coarse and fine-grained cause of death. Okay, this is a very comprehensive study. Okay, then here to the methodology that we do use here in this kind of investigation is to take as ansatz that the quantity scales with the size according to a power law. See here, n represents the here in our case the population of the size, and y represents the one urban indicator. But if you do it with the allometric studies of the organisms, if this n would be replaced by the mass of the organ, and here the observable that you want. So you have to do actually just transform this assumption into this equation, and then you have to fit and find both these quantities, the log of y null that we often call as alpha, alpha and beta, okay? So we use regular least square estimation, and in the first work, we also did nonlinear fitting based on the Narayana-Watson kernel method, okay? Presence of heterogeneities can be thought be identified by different values of alpha, okay? Or if you can do also, even if you know that some, for instance, in the case of the health outcomes in US and Latin America, we consider that these countries could have some specificities. So instead of presenting just one constant here, alpha, we introduced another one that accounts for different properties of each country you are taking the city from. Okay, when you do just one analysis, okay, and that's the way we have also provided. And this kind of approach can also be used if you want to make a scrutiny for the population, the population groups. Okay, here we divided into 3 population groups. Okay. Then I'm going here to talk about Brazil. Here is a map of Brazil. The colors indicate the geographic regions in Brazil. Okay, we divided officially in 5 big geographic regions. Okay, north, northeast, middle west, southeast, and south. That's where I am in Salvador here. It's the southmost state of the northeast. Okay, and here is the most developed part of the country. São Paulo, Rio de Janeiro. Brazil is border to southeast, but actually Brasilia is located in the Middle East. Okay, and here the south part of Brazil. Regarding the number of cities, okay, that are the number that I show here. Northeast accounts for 32%, south 30, southeast 30%, the south 20%, and north and Middle East 8%. Okay, I want to show here how the evaluation, the evolution of the urbanization process in Brazil along the years. Okay, from northeast from 1940 to 2010. Okay, here colors indicate the region. Okay, the most urbanized region is the southeast, and to share the less urbanized, the north and northeast. Okay, and about the share of here's the concentration of the population in cities above 100,000 inhabitants, also leading position of the southeast. From an economic point of view, the southeast account for more than 50% of the national GDP. Okay, there has been a small decrease in the last years, which was explained by the growth of other two regions. Okay, the south and the south and the spring, okay, and the Midwest here, okay. The Northeast has been almost without variation. And here is the share of the population, also the evolution along the years, okay. To proceed with a scaling analysis, we took some indicators, okay, that could cover wide aspects of living in city. We consider economy, violence, infrastructure, and technological standards. Okay, the variables that we used were the GDP for economy, number of homicides for violence, infrastructure, the length of the water distribution system, okay, and technology, we took the number of high knowledge employees in the service sector, okay. So we are going to present results for these four indicators. And we also do proceed with a characterization about the heterogeneity between the Brazilian regions and also within the Brazilian regions. We call this SSH, stands for spatial stratified heterogeneities, which is defined like this, okay? And N and NI, the number of cities, and also the variance. It's here easy to say that if all regions share the same sigma, okay, it's the same, this is a common factor, and these results, the sum here, this factor is 1, so that Q is 1, okay? So if would be the case, and where all regions, okay, share the same kind of heterogeneity, okay? So we explain here what's Q rate between the variance within global variance, as it was clear in the last slide. Q less close to 1, okay? You have this condition where the heterogeneous within regions are more alike than between regions. On the other hand, as I said before, if the heterogeneity in the case Q is 0, the heterogeneous between regions would be equal, okay? So it's when it lies in this region here, it's more similar than those within. And here you see what the result we found, okay? They are most likely to lie also all in this region here. But anyway, you find larger Q values for the infrastructure and service technology, okay? Larger this difference than when you consider the GDP and homicide. That's to say, here, although they can occur at different levels, the heterogeneity is among the regions when you consider different regions are more similar than within regions, okay? Here I'm going to show some of our results. Here are 4 different scatter plots that we obtain for the different variables, GDP, homicides, and here the infrastructure and high technology sector. You see that this kind of fitting, the linear scaling fits provide those scaling, okay, those straight lines, the slope of which reflects the value of the scaling exponent, okay? And then we proceeded also with a nonlinear adjustment made by the kernel procedure. And you see, for instance, here that is somewhat very good. Here you find a small discrepancy, a large discrepancy here, okay, and here also. So that we found those scaling exponents. As for their values, we see that the GDP is larger than 1. That means that the GDP per person at larger cities is larger than in smaller cities. This is a very well-known effect and is one of those advantages that were listed in my first slides, and justifying why people move to live in cities, in the expectation that cities will provide a better standard, better quality of life if you measure quality of life here by the wealth, the GDP. On the other hand, you also find this kind of results, that violence also increases superlinearly. Here we use the terms superlinear or sublinear according to whether the exponent beta is larger than 1 or smaller than 1. Of course, beta equals 1 is the linear case, okay, where the indicators are insensitive to the size of the cities, okay, and then that's what we get, okay. The infrastructure here is the length, okay, of the water supply, okay, and we see that it scales sublinearly, okay. This is also a well-known effect because it just states that if you put some pipes into the floor, they will serve much more people, okay, then if you in a city which has a higher density, higher populational density than if you live in a smaller city. The same amount of a kilometer of pipe will serve more people in a large country, in a large city, and then that's it's expected this kind of value. And finally, regarding the educational, here's the high technology sector, okay? This is closely related to educational opportunities and the attractiveness of cities for high-skilled people. You see the largest value of the exponent, okay? Beta almost 1.54, okay? So this is these trends are somehow expected, okay? But then we can now proceed how to compare how they are vary inside the regions and along the time, okay? First of all, you see the exponent here for the southeast is close to 1.2, and for the north is close to 1.4. Okay, but you have to consider south. The most rich region is the southeast, and the poorest would be the northeast, as I said to you. On the other hand, the GDP in southeast is similar to the south, which is here shown in cyan. Okay, so you could expect that the exponent of south and southeast would be closer, and they would be different from northeast. And this is not the case. You see that the southeast has the closest value to those of northeast, and far different from those in south. Okay, this is so to say, how the difference emerge. Although the value of the GDP is higher, that means that alpha, that parameter alpha, when we evaluate for the southeast, has a larger value and close to that of the south. Okay, the exponent, the way they grow, they vary with each site is different. Okay, in this there is a huge difference between south and southeast. Okay, although they share almost the similar GDP per capita. Okay, so this is things that appear in scaling analysis that somehow get lost if you do not carry this kind of investigation. Okay, there's also some relationships here with northeast and so on, but the most striking one is this south compared to southeast compared to northeast and compared to south. Okay, regarding the homicides, okay, they are also superlinear. Okay, the most violent, the region where the exponents for large exponents, that means the difference between small rates of homicides in small and larger cities. The most different is in northeast. Okay, in the southeast you have this kind of behavior. Okay, and then it has started to decay. Okay, possibly people is trying to argue that it's not the fact that the general homicide rate is decreasing, but that homicide is spreading into smaller cities, perhaps because of organized crime and so on. Okay, but this is somewhat expected result that has been obtained for all the other countries, but we have found similar results. Here also the two other, oh yes, what I would like to mention is that there is relatively weak dependence on longitudinal dependence with time. Here there are some more fluctuations in the a long time in the high technology service. Okay, and also you find as regard to city infrastructure of the water distribution system, the most different is in the northeast region, which is also the less urbanized in the north region. Sorry, in the north region, in the Amazonia area, where you have a very poor water system, even in the smaller, in the larger cities. Okay. Okay. I think I mentioned the most important aspects of these slides. Here, I should also point that the discrepancy in the northeast is the largest value of the beta exponent, showing also here that the larger cities offer attract much more the population, the high skilled population, than in other cities. You see, if you see the South region with the smaller exponents has a tendency to be more uniform across their cities. Okay, then I'm done here with the first part of my presentation, and I'm going now to talk about the I'm going to talk now about the mortality results. Okay, here I mentioned briefly the data sets. Okay, the Salomon project in US, the National Vital Statistics System and Census Bureau. Okay, and here we do, as I said, investigate the mortality. We group. We choose 6 different groups. 3 groups of specific diseases, is 3 groupings due to external causes, which generally call injuries. They are these in the first 3 groups: communicable, maternal, neonatal, and nutritional conditions, this CMNN, cancer, and cardiovascular and other non-communicable diseases. Okay, there are the 2 sets of diseases that we search for mortality cause, and the injuries we also divide into 3 injuries, 3 kinds of injuries, what we call non-violent injuries, road traffic accidents, or other unintentional injuries, okay, suicides and homicides. These are further subdivided into 41 fine-grained subgroups. These are a summary of our results, okay? And here they are divided by US and Latin America, okay? Here you can see the scatter plots. The reference line in red here is the case of linearity, corresponds to beta equal 1. So everything that stays below, when the straight blue line stays below the red dash line, you have a sublinear behavior, and when it stays above, okay, it's a superlinear behavior. Okay. Our findings, you can see that there are more. The difference between the betas here and the straight lines is more smaller than in the cases of the infrastructural results that I just presented here for Brazil. In some places in Latin America, the blue and the red line just superpose here. For this first group of disease, the CMNN, the cancer, and the non-communicable diseases, the US has we can see that it is sublinear, although in the Latin America it's very, very, very close to beta equal 1. Okay. In the case of suicide, non-violent injuries and suicides, is also a usual pattern. In the case of homicides, also, as I said, we had already detected that for the case of Brazil, which is also observed here for US and for Latin America as well. You also can see that there are several differences in the way the data sets are scattered, like here, or aligned in a straight, aligned into a straight line. Okay, this is we are going to make a point about that when we evaluate the variance of this distribution of points with respect to the straight line. Okay, now here a little bit of discussion. As I said, 0.9594. Okay, when you take all countries, include all countries, including US and the Latin America countries. Okay, but when you do by region, then we refer here to those results that I just comment in the previous figure. It's 0.94 for US, but very close to other countries. Okay. Now, then we go here into a fine classification. Okay, same NN in countries in US, sublinear but linear in US. Okay, sublinear scaling in as I said, in non-violent injuries in suicide for both countries, and superlinear for homicides in both countries. And also we did a final analysis considering we further divided the Latin America data into three for Brazil, Mexico, and Latin America minus Brazil and Mexico. We did that because you cannot do for every country if you have a small number of cities in your scale. Okay, and for this, because of that, we had to limit ourselves to the case of Brazil and Mexico, where the number of cities in the data sets were the largest, and then Latin America minus with exclusion of Brazil and Mexico. Okay, that's what we call other Latin American cities. And also the scaling behavior, you see also of homicides. Okay, they were for Brazil close that we indicated. And amazing to see that in Mexico it's somewhat sublinear and 1.1 for the other Americas cities. And we guess that this kind here is mostly related to the way criminality or organized criminality occur in Mexico. Okay, then it's another. As I said, we measure the variance. Okay, of the data as distributed, and we evaluate the goodness, the R square. Okay, in most cases they are up to 80% and even 99% for some regions. Striking exception was homicide in Mexico. Okay, as compared to the values in the other Latin American countries. Okay, it's interesting to see here that this is the scattering. This year we are measuring the scattering about the straight lines. This is also one major findings that we were somewhat surprised. This very low value of R square, and it's an indication of high variability in homicide rates across cities in Mexico, suggesting some stronger place-based effects. It's a general comment is as much the value of R square is closer than 100%, this supports the scaling hypothesis. Okay, that the general feature, the universal features, are the important issues to explain the values. Okay. Okay. I said, I think I have already said what we made a rank here of the values of beta, and saw that among different regions, they are mostly alike. That means those six types of disease causes, they are follow almost the same order with a few exceptions. The largest one is the homicide rate in Mexico. Okay.
Roberta, maybe take
Yes.
another 3 minutes to leave a little bit of room in the Q&A. Thank you.
Okay. Okay. I will then short here. I will.
No, you can go
I'm just
ahead. Yeah.
okay. Okay. But I am already discussing here the groupings that we did here. The rank of the beta exponents we did for has these general features, and here is the finer classification, as I said, with 41 different difference. You see, here is the the quadrants here in the horizontal axis is for sub or super US, in the vertical axis sub or super LA, and see how they depend with among others. You see that there are somehow clustered the specific diseases inside the specific 41 types of disease inside those six large groups. Okay. Okay. Here I just put for curiosity the largest and the smallest diseases exponents. Okay, in the case of US, LA, Brazil, Mexico, and LA minus Brazil and Mexico. The largest beta was HIV/AIDS, and the lowest one was the road traffic degree. Okay, these are the most increasing when sites increasing. For LA, it was violence and suicide. Suicide is also among the lowest. Here, LA minus Brazil and Mexico becomes also about. Interesting enough is tuberculosis. You see difference. Here in Brazil, it was among the largest individual cause, but it was the least individual cause for Mexico. And finally, here we see the dependence between the scaling exponents and the values of alpha. No? Here is alpha, and here is the beta exponents. They decrease systematically like this for the US and the variation. And here is the scaling the same. The mean square variance, the variance here as a function of the scaling coefficient. I would like to stress then here that the negative correlation between betas and alphas, that indicates what? That indicates the most frequent cause of death with those who have the higher intercepts tend to be more sublinear than those which are less frequent. Okay, this is an interesting find of our results. Okay, this negative correlation here between, that means the largest values of beta here, okay, occur at the values of smallest alpha. That means that they are less prevalent, they are less common. Okay, both in US and okay. And then this is what we stress here. And on the other hand, we have a positive correlation between the betas and the variance. And then the causes of death, the explanations, the cause of death with higher variability tend to be more superlinear. That means those graphs where there was a large spread of points, they are usually more superlinear than those graphs with a smaller scattering of data points. So I'm just about to conclude. Okay, it's also time to stop here. And so I'd like to just briefly mention that we are going ahead with this kind of work. Okay, the two further works are already done, and some more ideas to come. And so I'd like to thank you for your for your audience and interest. Thank you very much.
Thank you, Dr. Andrade. Thank you for the presentation. So I would like now to ask the audience. You're welcome to put your question in the chat. We have roughly 8 minutes for questions. You're welcome to put your question in the chat. It's a few of us, so feel free to sort of unmute yourself and ask the question. You can go ahead. Go ahead, Maurizio.
Yes, Roberto, thank you so much. This has been great. One question. So if you look at the database from CDC, is the data already assembled city by city, or how do you get the city? That's my question. Is it already there, or there is some post-processing required?
As I can tell you with more confidence what happens here in Brazil. Okay, the health system here in Brazil, they give we have data. Okay, with the death certificates with cause of death. Okay, the cause of death are indicated by those codes. I forgot now the name. The international cause of death. There is and then that's how you classify. Okay, according to whether it was cardiovascular disease, infection, cancer, and so on. Okay, so that's how we put our data together. I don't know here, Professor Usama Bilal in Drexel, he was responsible for doing the collection of the U.S. data. Okay, and so I for sure I cannot tell you how you in the U.S. make this kind of, but I suppose that it goes along the same document, the certificate, the death certificate document. Must contain what was the ultimate cause of death. I know that there are the ultimate, but also some influence the cause of death also. Okay, but I think that here we use the ultimate cause of death.
Thank you. Very good. Thank you so much.
Okay, thank you, Maurizio. Okay, that's the question.
Are there more questions? I mean, I have at least a few. If people want to take a little more time to collect their thoughts. So okay, so you mentioned you mentioned about the scaling of causes of death, beta, for the different regions, and how in one instance it could be related to organized crime. So could you maybe walk us through a little bit of what are the policy implications of your findings in that part?
In that part, I show here in Brazil, for instance.
Correct.
Okay, homicides. Okay, which is a cause of here when you draw just the exponent, it shows how inside one given region. Okay, it depends with the size of the city. A larger value, for instance, here in 2000. Okay, that would mean, for instance, that larger cities would be almost 20% more likely to have homicides than a smaller city. Okay, if you double the size of the city, the number of homicides is likely to increase by 1.2%. No, 20%. Now 1.2. This means increasing in 20% of But then you have to pay attention to the alpha, which is done here, for instance. Okay, the alpha says the level at which it starts. Okay, so that is why this kind of analysis here is very interesting. Okay, because it says that for instance, in the case of, if you consider, we did not do that, for instance, in the previous study, but if you consider this, and that would mean that a region with the same beta but different alphas, they have different rates of homicide. Okay, and if along the time, okay, the beta decreases, the only thing that you can say is that the number, the disparity about the rate of homicides is decreasing. You would have to take into account the value of alpha. If the value of alpha remains the same, then you'd say, okay, overall inside that region, okay, the number of homicides now is decreasing. The difference is decreasing from the beta is decreasing, indicating that in larger cities, the number of homicides have decreased, while in small cities they remain the same. But it can also be the opposite. Okay, the number of homicides in the big cities remains the same, but the crime spreads out into smaller cities. So that's why it's always necessary to account for both when you do a kind of time, a longitudinal study here, okay, like that, you would have to know whether this decrease in the southeast, for instance, the value of beta in the southeast, is because the number of homicides in the same in the larger cities remains the same, okay, and or that would mean a decrease would indicate that the number of homicides in the smaller cities have increased, or vice versa. That's this kind of, and in the case of Mexico, being more specifically here, okay, this is really something very interesting, because you see both the exponent is below 1, okay, and also the scattering of data, okay, is also, and that's why it's very it's a hint. Okay, I'm not telling that I prefer to think this as being a possible explanation, but I cannot inform and precise this. It's a finding that would deserve more accurate research.
Thank you, Dr. Andrade. So I see that we are right on the 1 p.m. mark. I don't see any hands up, so let's.
Avram, can I follow up something? Just what you
Sure.
are. Just a quick question. I mean, it looks like all these results can be a artifact of how you aggregate your data. I mean, the crime rate. Why does it have to do anything with the size of the city? This is how you're aggregating it. So I take different neighborhoods in a city. And then you see different crime rates. So when you aggregate over the city, you're just assuming that it's uniformly distributed, which is not true. We know that from studies. So this result that the crime rate is related to the size of the city doesn't explain much about the crime. No, so
Okay.
so this is, I mean, you have to disaggregate your data, and you have to look at the result, how it's changing by disaggregating and looking at different sizes of, you know, cells, basically. So
Thank you for your comment. I would like to perhaps what I'm going to say now may clarify your and complement your observation. The shallow bow data set, they has 3 definitions of cities. Okay, most of the way the issue that you mentioned is referring to how we define a city. Okay, and you can define it by as politically. Okay, this is where you choose your mayor and well, it's responsible for that city, or you can look for large urbanized, contiguously urbanized regions. Okay, and when we are doing here this result, I did not explain that in detail, but these results were obtained for taking the definition of cities as a piece of continuously organized municipality. Okay. So, for instance,
but they're not socio-economically homogeneous. So
yes.
if you look at the census tract level versus at the some combined version of census tracts versus the whole city, you will see different correlations. And
yes, there are different, but when you put all them together, okay, and you take, for instance, the city of São Paulo, it consists of 20 municipalities. That's what we consider, okay? We do not consider each one of them.
And that's my point. If you consider each one of them, the result will be different, because if you don't, you're not controlling for those socioeconomic factors. So basically, you're aggregating at the very high level, and then you're seeing results that will not reflect actually what's on the ground.
But
they have to control for certain factors. So if what you could do, you could find areas that are socioeconomically similar and aggregate them together. They might be probably neighboring ones. But if you take all of them together, you're oversimplifying, and then you're over aggregating, in my opinion.
So we are 5 minutes in, and I want to be conscious of people's time. I am very happy to stay in the call and discuss maybe a little bit more, but I do want to take some time to while everyone is here, to thank our speaker today, Dr. Andrade. Thank you for joining us today and for making time for this. And I'm happy to stay maybe another 2 or 3 minutes if you're interested to discuss. Thank you, everyone.
Thank you.
You have my email address. You can write to me. Ferelampos has my address, and perhaps you can read him so that we can follow the discussion later.
Let me put it on the chat. Let me put it on the chat right now. Just a quick second to go to my notes. Here you go. Okay, so this is also for everyone who's interested to learn, but I can follow up with Dr. With the participants too. Okay, thank you, Dr. Andrade. Have a great day.
Thank you very much. Okay, thank you for the opportunity. Bye-bye.